Okay, YouTube, in this video we're going to be exploring finite geometric sums. And that is to say, what if we were to add up the first n terms of something that is geometric? That is to say, if we had a sequence here, it starts with the first term, our second term is the first term times our common ratio, our third term is the first term times common ratio again, and so on and so forth, all the way out to the nth term. The question really becomes, what would happen if we were to sum the first n terms? And I can tell you, as a matter of fact, we have an expression that allows us to find the sum of the first n terms without actually having to go find all of the terms and add them together manually. So we would say that this formula here for the sum of the first n terms of a geometric sequence is given as the sum, which is s subscript n, of the first n terms, and also given thusly. So we would say if you wanted to find the sum of the first n terms, you would get a1 times this 1 minus r to the n over 1 minus r. And I'm going to rewrite this. I'm going to say a1 times really 1 minus r to the n over 1 minus r. And I'm going to pull the a1 out in front. Nothing different about these. But we'd say that our common ratio here cannot be equal to 1. But if that's the case, all we need to know really are these things to find these sums. So we say our needs. We need to know a1, okay? We need to know r, and we need to know n. So we need to know our first term, common ratio, and we need to know n, which is the number of terms. Now, you have more room to write probably than I do, but I had to squeeze that in there. But if we know these three things, we could find the sum of the first however many terms of a geometric thing you wanted to find. So for instance here, it says find the sum of the first 9 terms of this geometric sequence. And so we're given the sequence here, and we have this expression that's going to allow us to solve for the sum of the first 9 terms. So let's go ahead and write this down. We say S9. Now, as far as what I've written up over here goes, we say, well, what am I going to need to know to find S9? Well, I said, well, we need to know A1, we need to know R, and we need to know N. And so in this particular case, we say, well, then the value of our first term is just this 2. And if we said R, well, what's our R value here? We'd say, well, let's grab a couple terms here. Negative 6 divided by 2 is negative 3. So we have our common ratio here is multiplying by a negative 3 every time. And our n in this particular case happens to be just 9. We're going to add together 9 terms of the sequence. So I'm going to put these in a box and I'm going to say, well, gee, we got everything we need here to evaluate this. Let's start with our value of our first term out in front. So our first term is 2. The next thing I'm going to do is I'm going to kind of load myself up here because I know that this happens every time I do a finite geometric sum. I get an expression that looks like this. So dropping in our r value, which is negative 3 here, negative 3, and our n value is 9, you can see that this is actually going to take maybe a couple steps to evaluate on a calculator. So my suggestion is just this. Let's start in here, and what we're going to get is 1 minus negative 3 to the 9th. Now, I would not skip any or take any shortcuts. I would write this exactly how you see it, because what I know is that negative 3 to the 9th is negative, but when I take away a negative, it becomes a positive. So for instance here, I get this on the top, and this is all over 1 minus a negative 3. So if I were to say divided by now 1 minus a negative 3, I would get this here. And so this is the value of everything inside the parentheses. Now we need to double this, so times 2. So all of this work I would have done on the right here by hand. I did on the calculator, but we get 9842. And so that is the value that you get. If you were to take the first 9 terms of this sequence right here and add them together, it would already be that big. Okay. So let's go ahead and take a look at just a couple more sums here before we piece out of this video. Checkpoint 5. Now I do this one on purpose, or I like this one, and I'm definitely doing it on purpose. But the reason why is because it's been written in sigma notation or summation notation. What I want to point out here is essentially this. This is the sum of the first 8 terms of this particular sequence. So the sum of the first 8 terms, they are just writing it as sigma notation. So it says start your first term, go to your last term. We can see that this is clearly exponential, geometric. So here's the deal. With the geometric sum, again, we need to know A1, we need to know R, we need to know N. So we'll start with our A1. A1 wasn't given to us per se, but we could find it. We could plug 1 into our rule here. So we get 1. And so we would get 2 times 3 to the first, which is really 6. And so first things first, our first term is 6. Now our R, what is our R? Now I got to tell you, this one is actually kind of given to us, but R is always the base of our exponent here. So in this case, I would get that the value of R is 3. Now if you're not sure about this, what we can do is this. We could go find A2, which would be 2 times 3 to the second power, which would be 2 times 9, which would be 18. And then we could say, well, then R must be equal to a2 divided by the term before. In other words, must be equal to 18 divided by 6, or the 3 that I just claimed that you get from its rule. So now n, we say, well, n in this case is going to be 8. We're adding together 8 terms of this. So with all three of these values, let's go ahead and piece this together. We say our first term has a value of 6 we determined, and this would be 1 minus blank to the blank all over 1 minus that very same blank. So our r value is 3. So we'll station those in there this time, and we get an n value of 8. So let's look at how this one is a little bit different when we put it into a calculator. So starting on the inside here in our numerator, we would get 1 minus, and this is 3 to the power of 8. So this is going to be overwhelmingly negative. And what we're going to do is divide by 1 minus 3. Now 1 minus 3 I know is a negative 2, so I'm just going to go ahead and hit divided by negative 2. So now we have our parenthetical quantity. We're going to take this times 6. So take this times 6. What we end up with is a positive sum, and it's 19680. 19680. So the sum of the first 8 terms of the rule, or the sequence defined by this rule, adds up to this. So